you are able to listen to me. Otherwise, please give me a sign. I will be your presenter today on this webinar, and I hope it's useful for you and clarify a few concepts. So let's get it started. But before everything, I want to thank Hans to give me the opportunity to host this webinar as well. So, and having said that, let's start to this presentation. So these are the main objectives that I've set for today's session. It's going to be 3 blocks. The first one is going to be an introduction to what are toxicology indicators in environmental assessment. We're going to go to explaining also which are those in life cycle assessment that are more common. And also in the first block, we're going to explain what are the limitations we may encounter when we use those indicators for inorganic substance. The second block on this presentation is going to be an example on how can these indicators pop up in a normal life cycle assessment. So we're going to explain which are the main outcomes you can have for these indicators in the second part. And the last part of the session is going to be 5 steps best practices to take into account when you are extracting conclusions and interpreting the results of those indicators in life cycle assessment. So I hope this is going to be a really practical session, and I hope you enjoy it. So let's start. So this is the first block, toxicology indicators in environmental assessment. First of all, let's explain why these indicators are important and why we should include them. So it's clear that the use of substances that can affect human health or the environment is a concern for society, is a concern for workers that work in industrial sites, and is something that has to be somehow reported and acknowledged. Of course, in industrial processes, the use of toxic substances or substances that may imply a concern is common and is one of the main things to address when we assess the environmental of an industrial process. There are several methods out there, some scores or indicators that really quickly they claim that can give you an idea on what is the threat the substance may pose to the environment of the human health. So those scores, of course, are quick and therefore are popular when assessing the environment on industrial processes. And even if it's better to have a really knowledge of how the processes in the environment occur or appear, the output of those indicators could be interpreted by the person that is developing this environmental assessment without having let's say, a PhD in toxicology. So you can actually have the reply of those indicators, and therefore that's why they are popular. So we have made a really rough classification on how these indicators could actually be organized. This is a project that Arche, a consultant, developed for ECI, and these are the 3 main types we could actually identify on this assessment that help us to go through assessment toxicology in industrial processes. First of all are all those impact methods or indicators of scores that actually focus on the intrinsic properties of a substance. So are those indicators that gives you a score or an indication of the toxicology of a substance just based on the properties of the substance. So the physical chemical hazards, the human health, or other environmental hazards, but just focusing on the properties of the substance. Then we have a second method, which is risk assessment methods or methodologies that helps you to identify the risk a substance may pose to human health or environment. So they not only focus on the intrinsic properties of the substance, but also how this substance is managed within the life cycle of the product to actually avoid that this substance poses a risk. So these risk assessment methods not only take into account the hazard of the substance, but also how the substance is managed within the life cycle, within the life tree or the life stages of a process. And then we have the third group of indicators of scores, which are those used in life cycle assessment methodologies, which main goal is not define the toxicology of the substance, but actually give a comparative potential between one substance or another. So these are, it helps us to define which substance with processes could actually have more impact than other in toxicology for health or for environment. And these are pretty much the three main distinctions we can do in these indicators. So just I put here some commercial names of these methods that perhaps are familiar with you. So definitely this list can be larger and larger, but for hazard assessment, perhaps green list, green score, green works, so toxic potential indicators are all those names that risk, cost, tox, and many others that you could encounter in available. Usually they are not for free, or you have to pay a score, and those are easy methods that help you to identify the potential hazard of a substance. Even can give you a score of how this substance is compared to another. So these are the first group. The second groups are usually assessments, or they are reports. They gather real data, and they are available or hopefully, and in a lot of cases, endorsed by chemical authorities. For instance, there are some risk assessments for substances, for instance, copper, available in the European Chemical Agency website. Those risk assessments are also, in most cases, reviewed by authorities for different countries. At least in Europe is the case sometimes, and they focus in the life cycle tree of a substance. So where is the risk in the production, in the use, and in the end of life. So these are, let's say, the risk assessment methodologies. And then the last group, as we described before, the life cycle assessment methods. Here you have names that could be familiar for you if you ever have used the life cycle assessment. So in most of the available software, you can choose which method or which you use when defining toxicology impact. So you have CLM, you have ADP, impact, Lyme, Lucas, recipe, Traxi, USTOX. So really the list goes much more beyond this, but this just to give you a taste of which are these names for these hazards. Just two are, it happened when using life cycle assessment toxicology indicators in general. It happened that sometimes when using a method, you have some conclusions that differ when using another method. So for instance, when using USTOX, you can arrive to the conclusion that process A is less toxic than process B, while when using recipe, the conclusion may differ. So it was a need to actually clarify which of these methods could be more reliable, and actually they are always, and I know all of them are always in a process of improvement to actually avoid that this continues happen. So just here there is a list of the most used or the most relevant methods that are available in life cycle assessment. And this list of methods is taken from the ELCD handbook issued by the European Commission in 2010. So in this book issued by the European Commission, this handbook, they actually explain the the most used life cycle assessment methods for toxicology. And not only that, they also score these indicators based on several criteria. So whether if it's endorsed by authorities, whether they have environmental relevance, whether they are robust, whether they are accurate. So they have the European Commission in this ELCD handbook give a view on how these indicators score. So after going through the insights of all of them, they've arrived to the conclusion that most of them are not robust enough, they are not endorsed, and they can have problems when using them. Except by USTOX, which was the method considered to be better when using toxicology indicators in life cycle assessment. And the method USTOX is also being endorsed by UNEP CTAC. And inside the internal score that the European Commission defined in this handbook, the Commission decided to give level 3 to this method. So just in the down part of this slide, you can see an explanation of what means level 2, 1, 2, and 3. So 3 is there are only 3 levels. So 3, let's say, is the less reliable level. So even if USTOX was chosen to be the most robust method among all the others that take into account toxicology, even though USTOX is recommended but to be applied with caution. So what does it mean? We in this webinar, we will go through what means caution and how is our interpretation of that. So first of all, one of the reasons why this USTOX indicator was considered to be robust but still to be used with caution was because there are still main methodological challenges that remain open, especially for metal assessment. So what it means that there are inorganic metal compounds that for the intrinsic properties of the metal itself are more difficult to assess, as it's more difficult to assess the toxicology. These are the main key problems or main key issues that still remain open. I will not go through in detail. I will define in my next slides, I will explain what we mean by speciation, aging, and essentiality. But first of all, just to clarify, of course, the characterization factors that these toxicology methods have inside the method usually are calculated with incomplete data sets or data sets that actually cannot be, let's say, double checked. So that's, of course, one of the main problems of this method. And there is also a subjectivity when deciding one or other effects on how to translate those data that are still open questions. But let's go to the first one of the key elements of this challenge, which is speciation. So when metals are released to the environment, they get transformed. So they actually don't present themselves in the metal form, but also in other forms like organic complexes, inorganics, or hydrated ions. So it means that the effect of the environmental conditions of the receiving environment, let's say the amount of pH in the water, the amount of dissolved organic carbon in the water body that receives this metal, transform the metal form into different forms. This is called speciation. And these different forms of speciation differ in toxicology. So it means that while one form can be really toxic, the others may even be beneficial. And this is a characteristic of metals that is really complicated to model. And of course, it's complicated to be included when we talk about the global perspective of life cycle assessment. So taking into account that the speciation depends on the receiving body, the receiving environment, the conditions of the receiving environment, and the life cycle assessment usually assess the impacts in a global perspective. This intrinsic characteristic of metal speciation is difficult to integrate. This is one of the first challenges. The other could be the effect of time, so what we call aging. So those species that are available in the environment are those species that are available in the environment are with the effect of time decrease the concentration. So it means that with time the toxic potential may tend to decrease. This process is called aging because these species that are in the environment change form. For instance, they get insoluble forms or in not a soluble form, so therefore cannot be absorbed by biota or by fauna. And this process for which this happens among time is not fully understood, not fully agreed among the scientific community. Therefore, these complicated interactions are of course not included in usual methods of toxicology in life cycle assessment, which the consequence that usually the methods overestimate the effects of metals, the toxic effect of metals with time. So there is an overestimation by not including the aging. And the third and perhaps the most peculiar of the intrinsic properties of metals that are not included in life cycle assessment is the essentiality. So these forms of metals are needed for life, and these are essential components of cellulose and life. Let's say we all know that iron is part of our blood, but also copper and zinc. These are, and many others, are known to be essential for life. So the fact that those species are actually released to the environment doesn't mean per se that they're gonna create a negative impact. Therefore, it depends of the quantity, it depends of the conditions of the environment, it depends of the fauna of the environment, it depends of the quantity of this substance already present in the environment, what actually creates the fine line between toxic or essential. These thresholds of needs of different metals that are essential really depend on the receiving environment. And again, since life cycle assessment only assess impacts at the global scale, it's difficult and challenging to implement this quality of metal ions in this assessment, and therefore usually is not taken into account. With the conclusion that there is again an overestimation of the impact metal compounds create in the environment. So just to put you an example of how this toxicology relate with those, here is one of classical dose response graphics that toxicology use. This is really the classical one for essentiality, and you can see that at the beginning you may have at the beginning of the graphic you see that increasing the dose actually is good for environment. Then is an area on the graphic in which we call it essentiality, which the increases of dose does not affect to the environment, not to the species, not to the fauna, flora, because they actually regulate themselves to don't include them. And it's only at the end when actually this toxicity of these essential metals becomes a problem. So there is a range of um, a different response to the increase of the substance that are not linear. On contrary, are actually they are in this shape. So these are the main three key challenges when including metals in life cycle assessment indicators. So having had an explanation on which are the most relevant challenges and also the most relevant indicators on life cycle assessment, we come to the second part of the webinar, which is how can I interpret the results of toxicology knowing all this. So just let's start with this. So just to recap, even though we know and we have seen in the previous part of the webinar that there are challenges to this to the use of these indicators with metals, there is still advantages in using toxicology indicators on life cycle assessment. First of all, they are already implemented, all those methods are already implemented in normal software, so it's really, I will not say easy, but simple to just click and say, okay, in top of CO2 emissions or in top of greenhouse gas potential, I also want to know toxicology potential or ecotoxicology potential of my processes. So, of course, it's easy to have a first screening, and that has to be recognized. It could give you a global picture of where the main emissions or the main problems may appear in the value chain of the product. And it's also a good that gives you the opportunity to extract high-level conclusions. So how to define a little bit more this concept, let's go to an example. So this is really a standard example. I think everyone that has learned life cycle assessment perhaps has been faced with this. So is the a water desalination treatment plant. So water enters into the factory, into the facility, and it goes through different processes to actually change from salty water to normal water. So this is a really technical concept that you'll see that for each stage of this process, you may have some emissions, and you can also see which are the impacts that contribute the most to one or other processes. So taking into account this easy example, once you perform a life cycle assessment, the conclusions could be something like this. So you have used the normal software, you have normalized the results to see which actually is the most important, and you have this shape, this graphic, in which human toxicity and ecotoxicity are the most important. So please note that this is just an example, this is not real data, but that could be one of the normal processes you face when you use these indicators. So how can I have conclusions out of this? It will be perhaps too brave to say toxicology, human toxicology or ecotoxicity is the only problem, but it can help you to identify which are the most relevant processes. For instance, in this graphic, you see that between all the different phases of this process, disinfection, aquifer stabilization, reverse osmosis, microfiltration, all those have every impact category contributes to this process in a different place, and you see that human toxicology and ecotoxicology actually are in the same rates as the rates. So that could help you to actually enforce the use of human toxicology and ecotoxicology. Just enforce that reverse osmosis, in this case, or light gray, is one of the main processes for which needs better care, so which actually contribute the most to the rest of the impact categories. That could be one relevant conclusion. Second could be to use the most relevant life cycle stage. So if you not only model the process itself, but also the dismantling of the site and the construction and the service lives and the transport, you have a more holistic approach. You may also conclude that, for instance, in this example, human toxicity and ecotoxicity tells you the same as the rest of the impact categories, which service life, in this case, model for 50 years, is the most relevant life cycle stage. This is one of the questions or one of the conclusions you can take after the use of human toxicity and ecotoxicity. So just helping you to endorse what the other impact categories tell you already. So this, but of course, this is not enough. So we are just to help you to interpret better these results. I have put 5 easier steps to follow when interpreting the life cycle assessment results when it comes to human toxicity and ecotoxicity. These steps are meant to help users of these impact categories to have sound conclusions, and they are put in the shape of questions, as you will see in the next slide. So first step that we advise you to take is life cycle assessment and toxicology can help you to reply the right questions if you ask the right questions. So going not instead of if you put the question, what are the processes that may potentially contribute the most to harmful emissions? Human toxicity and ecotoxicity can help you to go for that. Which are the life cycle stages that contribute the most to toxicology impacts? That could be the first question that you could reply with the use of these indicators. Also, what are the list of substances emitted, and are those substances actually influencing the direct emission? So these are the questions that you may want to reply when using life cycle assessment toxicology indicators. So that could be the first step. So what will be the step 2 of your assessment will be checking the data sources. So it's been acknowledged that depending using one or other data sources, one or another model, one or other software, the results may differ. So if you have a toxicology indicator or human health indicator that actually tells you a different story as the other impact categories, perhaps the answer is behind the data. So which are the models behind this data? Are these reliable sources? So do I know which is the data? Is this data complete? Perhaps there's only few set of data and not the whole data, so I'm driving different conclusions because I don't have the full picture. And also, as we explained, for toxicology impact categories, are the model reliable? So we have seen that the European Commission has rated all those models. So am I using the last version? Am I using the version that is most reliable? Is a model score 1, 2, or 3? And also, which are the substances that contribute the most to this toxicology? Is a substance that is inside my process, perhaps comes to background process? So these are it will be the step 2. So clearly clarify which are those processes and which are those models. The next step that definitely requires your attention is the conclusions. So if I conclude that, as we've seen in our example, that the water purification, the step of the step of a reverse osmosis is the one that contributes the most to CO2 emissions or toxicology. Do I have real literature that actually support that statement? Here, we have to make a point. Perhaps you have to look into sources that go beyond life cycle assessment. So if you want to really reply that question properly, perhaps it's better to investigate outside life cycle assessment. Do I have a book? Do I know there's any research that actually confirms that reverse osmosis is the one that uses more chemicals that could contribute to ASAR, or those that use more energy? Is that true? Therefore, it's always important to check the robustness of the conclusions. Also, in the same line, if these conclusions are already reported, so do I have a report that says probably the needs for assessment are on this part of the process? Do I know that? Do I have a risk assessment report that says that? Do I have any other report that says that? So not only literature, but actually real endorsement reports by authorities. And first, and perhaps this is also important, so sometimes we have model data based on industrial processes or industrial practices that are not anymore in place. So do I know that? Am I using the right model, or am I basing my conclusions in obsolete assumptions? And this is important, especially when you are modeling processes that are not directly related to your process. So if you assume that you use commercial databases, be aware that try to use the most new ones, or those that guarantee you that industrial practices are up to date. And this is perhaps one of the most important steps that, of course, you may have to go to look into the metadata of these data to give robustness to your conclusions. Step 4 is avoid misleading statements. So don't agree in anything you're not 100% sure. So if you are developing a report based on life cycle assessment, you have on the use of toxicology indicators, and you have followed all the steps, and you are not sure that you can guarantee your conclusions, just be aware you put it on the report. If perhaps are limitations with the data, if perhaps are limitations with the toxicology study, perhaps within your screen of the metadata you have identified inconsistencies, or perhaps you are not sure the data you use is verified. In that case, be sure you include this in your statements and avoid to give misleading conclusions. So this is definitely one of the be always cautions with assessing A or B can be better based on toxicology indicators, and also identify those inconsistencies in your report. So that will be step 4 in the reporting phase. And heading out to the end of the presentation, just refer that perhaps it's always better to go beyond the use of life cycle assessment indicators and see what is outside already, what is already being used. So just to clarify, for copper use in Europe. So the European Copper Institute have made available a voluntary risk assessment for copper. So it means in this report, it assesses the risk the substance may pose within the production, the use, and the end of life, the whole value chain of the use of copper. So this voluntary risk assessment is done with real production data, with real techniques, directly measured, but not only the data emissions, but also the conditions of the receiving environment are taken into account. So all the specific conditions of water or the composition of water, the composition of soil is taken into account. Also is taken into account real direct emissions for companies that have decided, and industrial sites that have decided to participate in this risk assessment. And the conclusions and the process undertaken on this risk assessment is being agreed by the European Commission and verified by the Italian authorities. So this actually has been reviewed by European member states. So different countries, different experts for different countries in Europe have actually looked into this report and have agreed with the conclusions. As I said, under this report, the project acknowledges that even if there are exceptions to some observed industrial sites which could have a risk, in general, all the uses of copper currently in industry, the production, the use, and the end of life, doesn't pose a risk to the environment, health of the workers. So with the measures in place, there is not risk. So this is something always to refer. There is one for copper, there are more substances there are more processes there that you can always refer when you are not sure of your conclusions. Having said that, I'm about to finish this presentation. I still want to thank you for having listened to this presentation. There is at the end the slide. There is a list of reference that you can visit. But I believe now is the time to open the question hands. So